In this example, we're trying to find that initial population. We're trying to figure out what that C value is, because that's usually what we go after to begin with. And man, they really didn't really give us that initial condition. Would you give me a pen? Crying out loud. We get this value of 125 after 2 hours. I wanted at 0 hours for initial condition, so that's not any good. We also have this 350 bacteria after 4 hours. That's still not 0 hours. But we could plug those two values into our y equals ce to the kt. So that is y. Oh, nope. Actually, plug it in. So we have 125 bacteria. I don't know what C is. I don't know what K is, but I do know that this is after 2 hours. So 2K. We also know that there are 350 bacteria equals CE. I still don't know what those values are. I still don't know what K is, but I do know that after 4 hours, this is what's going on. Now, looking at this, we have two equations with two unknowns. We don't know what C is and we don't know what K is, but we sure would like to know them. So we need to solve one of these equations for one of those variables and then substitute it back in. So I'm going to solve this one for C because I think that would be the easiest thing to do. So then C is going to equal 125 divided by e to the 2k. Now, just to make my life a little bit easier, I'm going to write this as c equals 125 e to the negative 2k, because it's a lot easier to substitute in that product rather than substitute in that fraction thing. Okay, so then let's put that into this other equation over here. So we get 350 equals, put in our new C value of 125 e to the negative 2k multiplied by e to the 4k. Okay, well, hey, those two bases match, e to the negative 2k and e to the 4k. So let's put those together. So now we have 350 equals 125 e to the 2k. All right. Let's get rid of the 125. So divide both sides by 125. Uh, 350 divided by 125. I've got it over in my little notes that I've made. You can simplify that to 14 fifths equals e to the 2k. All right. I still want to try to get that k by itself, so I'm going to take the ln of both sides. So we get the so the ln of 14 fifths equals 2k. And then just divide both sides by 2. Whoop. So we get the ln of 14 fifths over 2 equals our k value. Which is nice, but unfortunately, K is not C, and C is uh, our initial population, initial condition. But we are at least a little bit closer. If we type this into our calculator, just so we can get like an approximation, it'll be easier to find our C value. We get 0.5148. I don't waste video time typing things into calculators. Uh, but let's figure out what our C value is, because now we know what K is. I bet we can find C. So we had found earlier that C equals, just so I don't have to scroll up, I'm copying 125 e to the negative 2k. So we can just plug this 0.5148 in for K. And then we get approximately 44.65. 0.543, which we can round to the nearest value. So we have our initial population, because you can't have part of a bacteria. You can only have a whole bacteria, or you don't have that bacteria. Population was about 45 bacteria. Done. In part B of this example, we were asked to write an exponential growth model for the bacteria population, which we've kind of actually already done. So I took this information from part A. K was 0.5418, so you can just plug that in for our K value, and our C value was 44.643. So you just plug that in for your C value, and that's done. There's our exponential growth model. However, it is kind of nice to be able to have a more precise version of this. So that's what we're going to play around with. So we've got our C value is all of this stuff, and our K value is this. So I'm looking to get a more precise C value. So let's just start by plugging in that exact K value into there rather than the decimal. So we get C is 125 e to the negative 2, and then our K value being the ln of 14 fifths over 2. But then if you look at that, it's like, oh, well, those two twos, they cancel each other out. So later twos. So then C is just 125 e to the negative ln of 14 fifths. You can bring that negative exponent, that negative, into the natural log, making it a -1 exponent. And that just means flip the 14 fifths. So now we have 125 e to the ln of 5 fourths, 5 fourteenths. Oh, and that e to the ln, those operations undo each other. So we just have 125 times 5 over 14, which gets us the much neater value of 625. Oh, 625 fourteenths. So that's our better C value. What we want to check next is, can we clean up that K value a little bit? Yeah, actually. So we could play with that K value here. Brown. So K equals stuff. So the ln of 14 fifths over 2. ln of 14 fifths all over 2. And then that 2, that's a K that divide by 2 is a 1/2, right? So ln of 14 fifths. So that 1/2 could be brought into that natural log and become a square root. So K equals the ln of the square root of 14 over the square root of 5. And you could simplify that because we don't like square roots in our denominator. So K equals the ln of the square root of 70 over 5. And we like doing that because then we get what happened up here, where the ln and that e are going to kind of clean each other up. So if we plug in our new values for K and for C, we get Y equals our C value that we got just a minute ago, which was 625 fourteenths. We get our E to our new K value that we just got, ln of square root of 70 over 5. Those two things are, oh, and then a T, and then a T. Almost forgot the T, right? We need a T? Yeah, we need a T. So then that ln and that E are going to cancel each other out. I'm worried I'm going a little crazy. Yeah, the ln and the E are going to cancel each other out. So everything's fine. We're all fine here. How are you? y equals 625 fourteenths multiplied by the square root of 70 over 5, all to the t. That would be a neater version. All right, so now what we want to do is we want to use those models that we've created in order to figure out some information about the bacteria. Here we want to check what's going on after 8 hours. I can use any one of these models. I'm going to use this one because I'm feeling frisky, so why not? I'm going to get a little bit closer though. So here we go. After 8 hours, that's my t value. So I just need to evaluate this thing when t equals 8. So we get y equals 625 over 14, e to the ln of 14 fifths over 2 multiplied by 8. So first I'd kind of cancel that 2 and that 8. So we get y equals 625 fourteenths, e to the 4 times the ln of 14 fifths. Whoop. Then let's see, the e to the ln of 14 fifths, that ln 14 fifths are going to cancel each other out. Well, not cancel, but they'll kind of go away. So we get 625 fourteenths multiplied by 14 fifths to the 4. Okay, a bit of a jump cut there, but we get 14 to the 4th and 5 to the 4th. I wrote it a little bit better for us. 625 is 5 to the 4th. So these two are going to cancel each other out. This 14 will cancel with the 14 to the 4th. It'll just cancel one of the 14s. So we just have 14 cubed. So y equals 14 cubed. So that's the only thing that we actually have to calculate. You type that into the calculator, you get 2,744 bacteria. Hooray! That's done. The next one, we want to know how many hours will the bacteria count be 25,000. This one, I feel like using that middle one just for something different. So we get 25,000 equals our 625. And I could use the one to the far side, or I could use the decimally one. It doesn't really matter. You just got to pick one. So we get the square root of 70 over 5 to the t. Okay, so I just want to solve that thing for t. I'm going to multiply both sides by 14 625ths. So this gets multiplied by 14 over 625. You do a little calculator, a little canceling. You end up with 560 equals the square root of 70 over 5 to the t. Okay, now to get that t out of the exponent, we want to take the ln of both sides. So we get the ln of 560 equals t times the ln of the square root of 70 over 5. So then you just need to divide by the ln of square root of 70 over 5. So t equals the ln of 560 divided by the ln of square root of 70 over 5. We type that into our calculator, we get a decimal approximation, which will be 12.29 hours. So after 12.29 hours, we'll have we'll have 25. We have a lot of bacteria after 12.29 hours. All right. So concludes our exponential growth and decay model. To keep in mind, you might get that dy over dx equals ky, but we can always just quickly convert that without doing any of the integration into y equals c e to the kt. C being our initial value and k being our proportionality constant. Thanks for watching. Bye-bye.